damage to the crystals during the compacting of the bed. It was also there to fill interparticle space and hopefully to cut down the gas phase diffusion component, gas phase flow component. The study was made for permanent gases through this medium. Now, you have, because particularly of the presence of the graphite, you have to take into account three components of flow. JS, the component of flow called into play by the presence of mobile adsorbed films in a concentration gradient, can now probably not be neglected. At least we didn't find that we could neglect it. So how is one to go about evaluating the three components and so getting the three diffusivities? Well, first of all, the crystals in the compact were hydrated. Therefore, this component was 0. So the total flow was the sum of these two. Now, in work of this kind, you want a calibrating gas. The usual calibrating gas that one assumes is to be non-salt, is helium. Now, of course, it's not strictly non-salt, although it is a very slight salt. But on the assumption that helium can be used as a calibrating gas, both JS and JI can be neglected, so the total flow is the gas phase flow of the helium. And from this gas phase flow, you can find the gas phase diffusivity of the helium. And from the gas phase diffusivity of the helium, you can find the gas phase diffusivity, always in the Knudsen flow regime, of the other gas. And this means that you can find Jg, the gas phase component for the other gas. And so, still with the crystals full of water, you measure the total flow. By means of the calibrating gas, you've been able to estimate the gas phase flow, and the difference gives the extra flow due to the mobile adsorbed film. Next, the crystals were dehydrated, and from the sum of the three terms, we know this, and we know this, and we measure this, we get Ji, and hence we get Di. And a typical set of numerical results is given in the transparency. You'll see that, as I said earlier, the nitrogen, dG, is of the order 10 to the minus 3 centimeters squared seconds to the minus 1. We did this twice. The first dehydration gave this set of values. The crystals were then dehydrated, the crystals in the compact were then rehydrated and dehydrated, and after that rehydration there was a small change in dG. The surface diffusivities came out to be of the order of 10 to the minus 4, and the intracrystalline diffusivities came out to be of the order 10 to the minus 6. You'll notice that these surface and gas phase diffusivities have a measurable temperature coefficient, and on a simple Arrhenius type interpretation, the energies of activation are those given at the bottom of the transparency. Now these measurements, as I say, are about the only ones I know of such a system. There are certain experimental uncertainties, but I think probably the right orders were obtained for the diffusivities. You'll notice, by the way, from the table that I just showed you, that the ratio of the intracrystalline diffusivity to the gas phase diffusivity lies between about 10 to the minus 3 to 10 to the minus 2. So if we know that ratio, what can we say about the important quotient, Henry law constant, times the ratio of these two diffusivities? Ki d prime I dg. Could I have the next slide, please? Just look at the right-hand side of this equation, this slide. Here are 5 calculated Langmuir isotherms for which the values of Ki, starting from the bottom and going up, are 50, 500, 1,000, 5,000 and 50,000. And you see, even for this range in values of Ki, you're getting the kind of isotherms which you measure in practice. So it would seem as though the quotient Ki times d prime I over dg could be quite large enough to find a reflection of intercrystalline flow. Now the last thing that I wanted to comment on, how about that time? Are time legs. I've already mentioned this and explained what I meant by a time leg, but there are 4 of these that are accessible to experiment. 2 at the ingoing face of the crystals and 2 at the outgoing face. For example, a membrane may be free of sorbate initially. We call the time lags measured under these conditions adsorption time lags, superscript A. And that at the ingoing face has the subscript 0, and that at the outgoing face has the subscript L. And the adsorption time lag, and I put it in inverted commas, is actually negative, corresponding to this line, for the adsorption time lag at the ingoing face. The outgoing face, as I've already explained, it's positive. Then you can also have the membrane containing a uniform concentration of sorbate, and you allow it to empty itself down to a steady state condition. Now we have 2 desorption time lags, and that at the ingoing face is positive, and that at the outgoing face is negative in this case. Each of these, as I've said, is accessible directly to experiment. The calculation of time lags when diffusivities are functions of the variables has the following history. Frisch evolved a method for finding the adsorption time lag at the outgoing face when D is a function of concentration. His method was applied by Topoulos and Roussis to the 4 time lags, again for the case where diffusivity is a function of concentration. And they obtained the results shown in the next slide, not for the time lags, but for certain time lag differences, which I quote here. The M infinity and the M naught in this particular slide are the same as the Q infinity and would be Q naught that I previously spoke of. They are the amounts finally in the membrane and initially in the membrane. The Topoulos-Roussis expressions did not contain those integrals IA and ID. And I will therefore refer to the origin of those. We have the slide off. Ash, myself and Edge were able to modify the Frisch method to derive all the time lags, not for such a limited case as diffusivity a function of concentration, but without reference to diffusivity at all. We found it possible to derive the expressions for all the time lags using only the continuity condition, which is simply conservation of matter. And I mentioned those integrals in the table. They have these values. But if we could have that slide again, you'll notice that these integrals are not involved, and in the last line you have a means of finding from flow experiments the value of, if you measure the final flow and you measure the 4 time lags, you can find this delta L. Therefore you can find the equilibrium uptake in the membrane. And you can do this only from flow experiments. You don't have to dismantle the membrane, take it away and do separate sorption runs on it. Moreover, because we have derived these time lags and these time lag differences using only the conservation of matter condition, the results are entirely independent of any equation of flow you like to postulate. For example, if you want to postulate a fixed law mechanism, the diffusivity can be a function of the variables distance, concentration, and time, either altogether, separate, or in non-separable functions. So the results have total generality, requiring only local equilibrium within the membrane between its heterogeneous parts, for sorption between its heterogeneous parts. There's one study of the use of this method carried out by Ash, myself, and Dr. Edge. If we could have the last slide. Can you focus that a little? That's better. Now, this was done by measurements were made by flowing these gases through a graphon, not a zeolite compact. The principle, however, is just the same, whatever the nature of the compact. In the third column are given the amount sorbed in direct equilibrium measurements for these gases at various pressures. And in the fifth column are given the quantities sorbed at equilibrium as determined entirely from the flow measurements at comparable pressures. And you see the time lag method, which doesn't require you to dismount the membrane, take it away and carry out separate measurements on it. Time lag method does give a very good result. Well, that's as far as I propose to go. I hope there'll be material in this talk which some of you at any rate haven't had occasion to come across before. I believe membrane methods, as well as transient flow methods, such as the rectangular boundary and so on, deserve attention from those who study flow processes and kinetics in beds of zeolite. Thank you.
what I might call the definitive treatment, overall treatment. Very, very impressive. And we have a few minutes before the next talk, which is scheduled to take place at 20 past 10. Is there anyone who would like to testify?
Strictly speaking, the flow should be determined by a chemical potential gradient. And you can electrically mention the activity coefficients. For example, with the rectangular isotope, even though the concentration seems to rise, it's not changing appreciably. If this be said of the chemical potential.
Certainly not. Chemical potential gradient is, as you said, really a better measure of the driving force. And of course, the quick treatment works in terms of concentration. And but then also you will notice that I pointed out that the evaluation of time lags is totally independent of mechanism. All you require is that the molecules should move. In the case of the rectangular front, the transport in the crystals under the conditions I postulated is negligible, and the flow is in the gas phase. Here, of course, activity gradients, concentration gradients, concentration measures activity.
So it may work out in practice, but in principle, it seems to me you could have the chemical potential gradient, even though there is no variation measurable in C/I. Therefore, in principle, there should be some degree of flow in the region of the horizontal flow produced by a measurement. This was what I was getting.
Yes, I think that's a reasonable comment. And that's why, as I've said, I introduced the condition requiring the diffusivity modified by the evaporation barriers to be extremely small. That is, I require the true intercrystalline diffusivity to be very much less than the effective diffusivity is modified by the evaporation barriers. That's not so unreasonable because the conditions for this type of behavior are that the isotherm must be very rectangular, and as we saw in the case of the alkanes, this implies a very high heat or energy of desorption. But it is a limiting case.
In the highest degree of rectangularity, I suppose there is also the risk of fusional effects in upsetting a local equilibrium.
Well, if that's the case, you're moving towards the sorption conditions that I described subsequently. And those are not the conditions, as I emphasized throughout, that I'm proposing. You may, in this context, it is more probable, or it's easier, to get local equilibrium where the fluid is only being adsorbed on the external surfaces of non-permeable crystals. So in order to come close to or achieve the condition of local equilibrium, the crystallites need to be small, and the true intercrystalline diffusivity needs to be large. That also introduces the probability of a greater influence of evaporation barriers, because you've got more evaporation barriers per unit length of bed.
So there's a compromise.
Well, it isn't necessarily a compromise. You saw you can simply put in the modified diffusivity into the general equation. It doesn't modify the form, but it does modify the value of the diffusivity.
Is this relation to non-uniform crystals?
Well, you're really moving now towards what used to be called persorption. According to J.W. McBain, if we go back long enough in time, you're not talking of a homogeneous medium, but one like microporous carbon, where there are pores of different sizes with introducing different flow characteristics. I think here you simply have to lump the whole lot together and find out what the resultant is. And in the case of the crystals, you can still ascribe part of it to the crystals, however they may be inhomogeneous, and part to what happens outside the crystal. But it's a point, you're moving towards heterogeneous media.
The papers that have been published recently describing the surface barrier to damage in the crystals, do you think that it really is this evaporation phenomenon as the era of the true description?
Well, it depends what the diffusing molecule is. If it is a diffusing molecule with a very high heat absorption or energy absorption, then I think you must always have in the back of your mind the possible significance of an evaporation barrier. At that place I had a different explanation. It was that something happened to a very thin layer of the surface of the crystal which changed its diffusion properties from those of the body of the crystal. Whether that's proved or not, I don't know. I'm waiting for a definitive proof. I don't know whether I perhaps don't feel that one has yet been provided.
Well, just two more questions on that.
Professor Barrett, I agree with you that the membrane method is very effective. I think we presented some work Reno on diffusion silicon crystals. I'd like to follow up the comment on the surface barrier effect. The heat effect of the surface barrier, I think that their result to an experiment about the same is hard to differentiate between the two.
Between which and which?
Between the evaporation effect and surface barrier effect. If one was to do a gravimetric experiment with different sized crystals and correct the diffusivity obtained by both, one would find that the diffusivity increases with crystal size and plateaus off. That can both be explained in terms of evaporation barrier and surface barrier. I'm wondering if there is a way with either a membrane experiment or with a gravimetric experiment to differentiate between those two.
Between an evaporation barrier and a surface skin.
That's correct.
Well, unfortunately, the treatment appears to give a very similar kind of expression to both. So it may be quite difficult. But if you could, the limit of a bed of powder is a single crystal. You could mount a single crystal and study the flow through that. It would be improbable that the effect of either would be very significant. Certainly, I don't think the effect of the evaporation barrier would be, because you have millions of unit diffusion steps inside the crystal, and only a single evaporation is the exit place to a single crystal. The skin, however, could be thick enough to ruin permeability altogether. So on that basis, if you still found a permeability for a particular crystal, single crystal, which was very much less than the permeability for another one of similar dimensions, you might suspect either there's a lot of detrital material or there's damage to the surface which has created the skin. In that sense, you might differentiate. Incidentally, there have been measurements made, as you may recall from the Reno conference, using single crystals of cloudicite, But these produced a number of complications which really made the results extremely difficult to interpret, so I don't think they would have helped. But it is an obvious and worthy subject. We would like to be able to differentiate between these effects. We don't know how as yet, I think.
Last quick,
in case of a non-equilibrium case, there are the temperature changes in the bed. What effect would that have in the order of magnitude? Would it change your, if you assume that's thermal, including the temperature changes, what kind of effect?
Well, it depends which part of my talk you're referring to. If you're referring to the last part, equilibrium measurements from time lags, as I explained, the results, assuming local equilibrium, which will change, of course, as the temperature alters, you should still get the M0 is the amount initially solved at a known temperature.
Now, how about calculation of diffusion?
But for other parts of my talk, temperature variations would, of course, change rates. And the assumption is isothermal flow. And of course, in beds, you may not achieve isothermal flow. What you're indicating is the several problems which people who study kinetics absorption are almost bound to run into. There is, of course, if one is studying absorption kinetics, I mentioned a criterion for getting the right boundary conditions is that the half-life time for flow in the gas phase in the x direction of the solution should be very, very much smaller than the half-life time for flow into the crystal. This, in effect, means that the half-life time for flow into the crystals is very protracted, very long. If you want to eliminate the effects of non-uniform temperature, then you must have very long half-life times for the absorption process so that any heat generated has plenty of time to be dissipated.
well, thank you very much. I think we must stop there. It's been a fascinating experience, and I'd like to express Right, but we